Okay, y'all, so what we got now is problem 515. So if T is a self-adjoining operator on a Hilbert space H and K is a compact operator on H, then sigma of H plus K minus sigma of H consists solely of isolated eigenvalues of a finite multiplicity. So this problem kind of screams an algebraic approach because you see that H plus K, and we've got that the compactness, so it feels like we're going to be working in the Fedholm operators, but also it's very topological because we're talking about isolated points. So the solution to this problem, we're going to build up the concept of a Weyl spectrum, and from that it will have a solution based out of something called Weyl's theorem, which we'll get to in a second. So and it's going to kind of involve a little bit of algebra, a little bit of topology, and a little bit of analysis. So it's going to be a nice mix of everything that we've seen, all the methodologies that we've seen so far. So first off, we're going to say let's T be self-adjoining for this problem, and we're going to note that for 1, we only need that T is an operator, our lemma 1. But obviously for the rest of the problem, we're going to need it, but note that we're not relying on the self-adjoinancy of T when we are proving lemma 1. So, first off, we're going to note that omega of t is going to be the set of lambdas in the complex plane such that t minus lambda 1 is not Fedholm 0. Now, what you're going to note here is that we also have a second definition where it's just not Fedholm at all. And that's going to be sigma t hat. But when t is normal, we get that these two constructs are analogous. And this follows from the fact that the dimensions of the kernels are going to be the same when you have a normal operator. So for the remainder of this problem, we're not really going to use this notation because they're equivalent, but we wanted to bring it up because that allows us to work more generally with Fedholm operators and just say, oh, well, it is Fedholm, so instead of having to prove every time that it's of index 0, because that's going to follow from the fact that we have that it's normal. Then the next concept that we're going to need is going to be pi double 0 of t, which is the set of lambdas such that lambda is an eigenvalue of finite multiplicity. So this is going to be our isolated points in our spectrum. So what we have next is going to be lemma 1, and lemma 1 is that that if you have some operator t on a Hilbert space, and that its Weyl spectrum is going to be a subset of the spectrum of it plus any compact operator. So what we have here is that if we start with an element of t plus k, and we subtract off some lambda and it's invertible, then we can rewrite it in this form here by basically just anti-distributing k. Now, what does this give us? If we have some invertible element s, then s plus k, we can do the same thing by anti-distributing our s, and we get that this piece right here is obviously Fedholm of index 0 by definition, because I plus k was Fedholm of index 0. So what this gives us is that when we do this here, right, we have that we can claim, because this is invertible, we have that is a Fedholm index 0, which follows directly from this line of argumentation here. So what this gives us is that if lambda is not in our Weyl spectrum, then, because it is of Fedholm index 0, we know it's not in our Weyl spectrum. And if we have that it is not in our spectrum, then lambda cannot be in the Weyl spectrum, which is equivalent to saying that that the Weyl spectrum is in fact a subset of the spectrum of t plus k as desired. So now that we have this lemma here, we're going to combine it with the statement of Weyl's theorem here. So real quick, I want to go over to this diagram after we look at Weyl's theorem to kind of get a picture of what we're working with. So what it says is that Weyl's spectrum is in fact just the regular spectrum with the isolated eigenvalues removed. So what does this tell us? This tells us that if I have the spectrum of some element t, that it can be broken up into two parts. That we have its Weyl spectrum here, and we have its isolated eigenvalues there. Now, why do we get that this is in fact in the intersection with the spectrum of t plus k? Well, that's going to be right here. Right, that's going to be our lemma 1. So what this gives us is that we can construct the diagram in this way. And what we need to show to finish the proof is that it in fact we can do it in the other way as well, that this is symmetric, that this thing here, that everything other than the Weyl spectrum of t is in fact just pi double 0 of t plus k. So how do we go about proving this? Well, first off, we're going to combine lemmas 1 and we're going to combine lemma 1 and Weyl's theorem, which all we're going to do is we're just going to replace this here with our Weyl spectrum. So we're going to end up with this inclusion there. And then the next thing that we're going to do is note that this implies that the Weyl spectrum is in fact the intersection of those two, which is what we showed before. And again, that's going to follow from that statement there. And so now what we want to do is consider what happens when we have something that is in that yellow region, that is in here. So we're going to take a lambda that is not in the spectrum of t, but is in the spectrum of t plus k. And what does this tell us? Well, this tells us that t minus lambda must be invertible, right? Which tells us that t minus lambda must be fed home. And again, that's going to follow from our discussion with the diagram and the fact that it has to be in the middle. So what we can now do is we want to find what the adjoint of our t minus lambda is. So we go through a quick computation right here. Just break it up, use the extract our lambda, put it back in the second term as a complex conjugate, and because t is a self-adjoining operator, it just moves across easily, and we get that the adjoint of t minus lambda is just going to be t minus the conjugate of the complex conjugate of lambda. So what this gives us is that I can in fact commute the two operators. So we get that t minus lambda is also normal, which gives us that it is in fact in the Fedholm 0 set, which tells us that we get that it is in Fedholm 0 since we've already shown that it is Fedholm. So what this tells us is that it is, because it's normal, it is in the Weyl spectrum. So if we go back and use Weyl's theorem but instead of plugging in t as our thing, we're going to work with tk. So we're going to get 4 here. And what we see is that because this guy is normal, we get that we get this statement here. We get that that the Weyl spectrum of t plus k is actually equal to the Weyl spectrum of t, and that's because they both have to be in the intersection of the spectrum of their spectrums. So what we can now do using that is that since we have this equation here, we can consider the difference between the two spectrums, which we can then replace with the difference with its Weyl spectrum, because again, the difference between these two guys by Weyl's theorem and our subsequent analysis has the The things that are in here that are not in here are solely outside of the spectrum of t plus k. So we can do the replacement in that equation without a problem. And then we've shown that this is actually equal to this guy. So what we've done is shown by Weyl's theorem that this is going to, in fact, be inside of the, because we remove their intersection, we get that it is inside the isolated eigenvalues of finite multiplicity, but that's exactly what we were looking for, is that sigma of t plus k minus sigma of t is finite, are the finite eigenvalues, are the eigenvalues of finite multiplicity that are isolated within our t plus k. So that completes the proof. I hope you guys have a great summer, and I will see y'all next semester.